Tonight, two numbers, and the distance between them is the whole story. Here is the first. Somewhere between 100 billion and 400 billion stars turn in our galaxy, and we now know with real confidence that most of them have planets. Run that arithmetic, and the answer arrives in the hundreds of billions of worlds in this one galaxy, and there are perhaps 2 trillion galaxies. You have heard this number, or something like it, and it is genuinely true, and it is the reason people say the universe must be full of Earths. Now here is the second number. The count of planets that human beings have confirmed to be genuinely like this one. A rocky world the size of Earth, in an Earth-like orbit, around a sun-like star. With an atmosphere we have actually measured. That number is 0. Not a small number, not a handful, 0. After 30 years of searching, after more than 6,000 confirmed planets, after 2 space telescopes built specifically to hunt them, we have never found another Earth. Not one. And here is the part that makes this worth a whole night of your time, because it would be easy to hear that as a disappointment, and it is not one at all. The reason the number is 0 is not that the worlds are not out there. The reason is far more interesting and much stranger, and it says something quite profound about the peculiar position we occupy as a species that has only just learned to look. Tonight, we are going to do something nobody usually does with this subject. Instead of touring the wonders, we are going to audit the number. Where does it come from? How do we actually find these things? What have we really seen? And what have we only inferred? And why does every promising candidate seem to quietly evaporate a few years after the headline? Now, let's begin. Before we go anywhere, settle in. Let your shoulders drop. Let the day finish falling away, and let your breathing slow to whatever pace it likes without you supervising it. Maybe the room has been dark for a while already. Maybe you are somewhere on a long shift or lying awake with a mind still turning over the day. Wherever tonight finds you, this is a good place to be. And nothing here requires anything from you. There is no argument to follow closely and no test at the end. If sleep arrives part-way through the census, let it. That is exactly what tonight is for. Let us begin with how astonishingly recent all of this is, because it is the fact that puts every other fact tonight in proportion. And most people have not quite absorbed it. For the whole of human history, through every civilization, every philosopher who looked up and wondered, every astronomer with a telescope, the number of planets known to exist outside our solar system was 0. Not few, 0. People had speculated for centuries, beautifully, going back to Giordano Bruno in the 1500s, who argued that the stars were suns with worlds of their own, and was burned at the stake in Rome partly for saying so. But speculation is not knowledge, and for 400 years after Bruno, the honest scientific position was that we had no evidence, none whatsoever, that a single planet existed anywhere except here. Every star in the sky might have been sterile and alone. We genuinely did not know. The first confirmed detection came in 1992, and it did not come from where anyone expected. It came from the wreckage of a dead star. A Polish astronomer named Alexander Wolszczan, working with the enormous Arecibo dish in Puerto Rico, was studying a pulsar, the spinning corpse left behind by a supernova, and he noticed that its pulses arrived very slightly early and very slightly late in a repeating pattern. Something was tugging on it. Planets orbiting a stellar corpse in a system that had already been destroyed once. The first worlds ever found beyond our own were, in a sense, ghosts. 3 years later, in 1995, came the discovery that actually opened the field, when 2 Swiss astronomers found a planet orbiting an ordinary sun-like star called 51 Pegasi. That one, too, was nothing like expected. It was a gas giant, roughly the mass of Jupiter, orbiting so close to its star that its year lasted about 4 days. Nobody had predicted such a thing. Nobody thought a planet could be there. The textbooks had a theory of how planetary systems form based entirely on the one system we could see, and the very first normal star we checked broke it immediately. That is worth holding on to tonight, because it is the pattern that will repeat. Every single time we have widened our view, the universe has said, gently, that our sample of 1 was not representative. And then the count began to climb, slowly at first, a handful a year, mostly enormous planets close to their stars, because those were the only ones the early techniques could catch. Then, a spacecraft changed everything. The Kepler Space Telescope launched in 2009 with one job. It stared, continuously and without moving, at a single patch of sky containing about 150,000 stars, and it measured their brightness over and over for years, waiting for the tiny dip that happens when a planet crosses in front of one. It found thousands. The count went from dozens to hundreds to thousands, and today the confirmed tally stands somewhere above 6,000, with thousands more candidates queued behind them, awaiting confirmation. In one human lifetime, the number of known worlds went from 8 to over 6,000. My grandmother was born into a universe with no confirmed planets outside this solar system. That is how new all of this is. So with 6,000 worlds in hand, why is the number of confirmed Earths still 0? The answer begins with a fact about our methods that almost never gets explained properly. And once you understand it, the entire shape of tonight's problem snaps into focus. We are not looking at these planets. Almost none of them have ever been photographed or seen in any sense you would recognize as seeing. A handful of very large, very young, very distant planets have been directly imaged as faint dots, and they are the exceptions that prove the difficulty. The overwhelming majority of the 6,000 were never observed at all. What was observed was the star. Every one of those worlds was detected as an inference, a disturbance in the light of something else. And the two ways we do it both have a bias baked so deeply into them that they were always going to find everything except a planet like this one. Start with the older of the two methods, because it was the one that found 51 Pegasi, and it is beautifully indirect. It is called the radial velocity method, and it works on a fact that sounds like a technicality and is actually rather lovely. A star does not hold a planet in orbit. A star and a planet orbit each other. They both circle a shared center of mass, and because the star is enormously heavier, that shared center sits very close to the star's own middle, so the star does not travel far, but it moves. A planet going around a star pulls the star into a small answering circle, a wobble, and if we are positioned to see that wobble side on, the star is alternately coming very slightly toward us and going very slightly away. And when something moves toward you, the light it emits gets crowded a little bluer, and when it moves away, the light stretches a little redder. You know this effect from sound, from the way a siren drops in pitch as it passes. Light does the same thing, and we can measure it with fantastic precision by splitting starlight into its spectrum and watching the dark absorption lines, the fingerprints of the elements in the star's outer layers, shift back and forth against the ruler of the spectrum. Jupiter pulls our sun around at roughly 12 meters per second walking pace, and instruments today can detect stellar motions well below 1 meter per second, which is slower than you are breathing. So the method is exquisite. But notice what it favors. The size of the wobble depends on the planet's mass and how close it orbits. A heavy planet close in yanks its star around hard and produces an obvious signal. A light planet far out produces a whisper. Earth pulls the sun at about 9 centimeters per second, which is the pace of a snail. And that signal has to be teased out of a star whose surface is a boiling, churning, spotted, flaring ball of plasma, with its own motions vastly larger than the thing you are trying to measure. Radial velocity was therefore always going to deliver a catalogue full of massive planets on short orbits, not because those are what exist, but because those are what shouts. The second method is the one that found most of the 6,000, and it is even simpler to describe. The transit method. If a planet's orbit happens to be lined up so that it passes directly between us and its star, the star dims very slightly during the crossing, and if you watch long enough to see that dip repeat on a regular schedule, you have found a world. The size of the dip tells you the planet's size. The interval between dips tells you the length of its year, which tells you its distance from the star. It is, at its heart, a shadow measurement. We find planets by watching for the shadow of something we cannot see falling across a light we can. The numbers involved are astonishing. When Jupiter crosses our sun, seen from far away, it blocks about 1% of the light. When Earth crosses the sun, it blocks about 1 part in 12,000. That is the entire signal. To find a world like ours, you must measure the brightness of a distant star to a precision better than 1 part in 10,000, repeatedly, for years, and then distinguish a real repeating dip of that depth from the ordinary flickering of the star itself, from instrumental drift, and from the thousands of other things that make starlight vary. Kepler was built to do exactly this, and it is one of the great instruments in history. But now here is the geometric problem, and this is the one I most want you to take from tonight, because it single-handedly explains a large part of the shape of our catalogue. The transit method only works if the orbit happens to be edge-on from our point of view. Think about that. Planetary systems are not aimed at us. They are oriented randomly, every possible tilt, scattered across the sky like coins tossed onto a table. Some face on, some edge on, most somewhere in between. If a system is tilted even modestly out of our line of sight, the planet never crosses the face of its star from where we sit, and it is completely invisible to this method no matter how large it is or how long we watch. The planet is there. It simply never casts its shadow in our direction, and the chance of that lucky alignment depends on how close the planet orbits. Work the geometry, and it comes out roughly as the ratio between the star's radius and the width of the planet's orbit. For a hot Jupiter parked a few million miles out, the odds are good, something like 1 in 10. For a planet at Earth's distance from a star like the Sun, the odds are about 1 in 200. Say that slowly. Even if every single sun-like star in the galaxy had a perfect Earth in a perfect orbit, the transit method would miss roughly 199 of every 200 of them, purely because of the angle we happen to be viewing from. Not because of instrument quality, not because of budget, because of geometry, permanently, forever. Layer a second constraint on top. To confirm a transiting planet, you generally want to see the dip at least 3 times, to prove it is periodic and not a fluke or a passing blemish on the star. For a hot Jupiter with a 4-day year, 3 transits takes under a fortnight. For a planet in an Earth-like orbit, 1 transit per year, 3 transits takes at least 3 years of continuous staring at the same patch of sky without interruption. Kepler managed about 4 years of primary mission before a mechanical failure in its pointing system ended that phase. Which means that for Earth analog orbits, Kepler was operating right at the very edge of its capability, catching the faintest possible signal, the smallest number of times, in the smallest possible sample of stars lucky enough to be aligned. So put the 2 methods side by side and look at what we have built. One technique that preferentially finds heavy planets close to their stars, another that preferentially finds large planets close to their stars and additionally requires a 1 in 200 alignment for anything at Earth's distance. Both of them are least sensitive by an enormous margin to exactly one kind of object. A small rocky planet, far enough out to be temperate, going around a star like the Sun. We built 2 magnificent nets, and the mesh of both of them is precisely the size that lets an Earth slip through. This is what statisticians call a selection effect, and it is one of the most important ideas in all of science, and it is the reason tonight's audit matters. A selection effect is what happens when the way you look shapes what you find, so that your catalogue tells you as much about your method as it does about the world. The classic illustration is the fisherman with a net of 4-inch holes who concludes, after many voyages, that there are no fish in the sea smaller than 4 inches. Every observation he has made supports his conclusion. His data is perfectly good. His conclusion is nonsense, and the flaw is not in the sea, it is in the net. So when you hear that the most common type of planet in the galaxy is a super-Earth, or that hot Jupiters are everywhere, hold it gently, because part of what you are hearing is a description of our nets. Astronomers know this perfectly well, and a huge amount of clever statistical work goes into correcting for it, into asking what population would have to exist to produce the catalogue we actually got, given everything our methods would have missed. That correction is the entire basis of every large number you have ever heard about habitable worlds, which means the honest way to put it is this: the billions are not a count. Nobody has counted billions of anything. The billions are an extrapolation from a small biased sample corrected by a model, and the size of the answer depends heavily on how you do the correcting. And when you look closely at how much the answers actually vary, the picture gets a great deal more interesting. Before we go on to the numbers, it is worth looking at what the 6,000 actually consist of, because the demographics of the catalogue are surprising in their own right, and they tell you something important about our position. If you sort every known exoplanet by size, the single most common category is a class of object that does not exist in our solar system at all. Planets between roughly 1 and 4 times the radius of Earth, larger than our world and smaller than Neptune, turn out to be the most abundant type we find, and quite possibly the most abundant type there is. We have no example. Between Earth at 1 radius and Neptune at about 4, our own system contains nothing whatsoever. The gap is total, and yet that gap is precisely where most of the galaxy's planets seem to live. Sit with the strangeness of that. For all of human history, we developed our intuitions about what planets are by looking at the 8 we could see, and it turns out the most typical planet in the galaxy is a kind we had never encountered. In a size range our own system skipped entirely. When astronomers named them, they had to invent the vocabulary, super-Earths, for the ones that seem rocky, mini-Neptunes or sub-Neptunes for the ones that seem gassy. And as we will see later, telling those two apart is one of the hardest and most consequential problems in the field, because from the outside they can look identical. The second surprise in the demographics is where things orbit. Our solar system is arranged in a way that feels natural to us. Small, rocky worlds close in, giants further out. Everything in nearly circular orbits, all roughly in one plane, all going the same direction. That arrangement is not the rule. The catalogue is full of massive planets in absurdly tight orbits. The hot Jupiters, giants whose years last days. There are planets on wildly stretched, comet-like paths that swing in close and then race away. There are systems where the planets orbit in a plane badly misaligned with the star's own spin, and a few where planets orbit backwards relative to their star's rotation, which is a sign of a violent history. There are systems packed so tightly that 5 or 6 planets fit inside what would be Mercury's orbit here, all locked into resonant rhythms with each other. Now, some of that is the selection effect talking, and it is important to be fair. Hot Jupiters are wildly overrepresented in the catalogue because they are the easiest thing in the universe to detect, and better statistics suggest they are actually uncommon, orbiting only about 1% of Sun-like stars. Compact systems of small planets are easier to spot than spread out ones for the same reasons we discussed. So, the catalogue exaggerates the weirdness, but it does not invent it. Even after correcting for every known bias, the honest conclusion stands. Our solar system is not a typical arrangement. It is unusual in several respects at once, in its lack of anything in the most common size class, in its lack of any planet inside Mercury's orbit where a great many systems put several, and in the neat, well-spaced, near-circular tidiness of the whole thing. Astronomers debate exactly how unusual, and the answer depends on how you measure. But almost nobody now argues that our arrangement is the standard model, which is a lovely and slightly vertiginous thought to hold at this hour. For 400 years from Copernicus onward, the story of astronomy has been a series of demotions from specialness. Earth is not the center. The Sun is not the center. Our galaxy is one among trillions. And then, at the very end of that sequence, we finally get to compare our planetary system to others. And the answer that comes back is not that we are ordinary after all. The answer is that we appear to be, in several specific and measurable ways, a bit odd. Not the center of anything. Just unusual in a particular corner of the possibilities for reasons nobody yet fully understands. And that matters for tonight's audit in a direct way. Because if our system's architecture is unusual, and if that architecture has anything to do with why this particular planet ended up stable and temperate and wet for 4 billion years, then finding a true Earth analogue means finding not just the right planet, but the right system around it. And that is a much rarer thing to go looking for. The number astronomers argue about has a name, and the name is a little piece of scientific poetry. They call it Eta Earth. Eta is a Greek letter used in mathematics for a fraction or an efficiency, and Eta Earth means roughly the fraction of sun-like stars that host an Earth-sized planet in the habitable zone. It is the hinge on which every estimate of how many Earths exist ultimately turns. Multiply ETA Earth by the number of sun-like stars, and you get your headline. So it would be reasonable to assume that after Kepler, after all those thousands of detections, we know this number reasonably well. We do not. And the degree to which we do not is genuinely startling. Published estimates of ETA Earth range, depending on the team and the method and the assumptions, from around 5% at the low end to around 60% at the high end. Some analyses land near 5 or 6%, others land near 10. Others land above a third. A widely used consolidated figure in the community sat for years around a quarter, and more recent work has pulled it down towards 7 or 8% for sun-like stars. Sit with that spread for a moment because it is the honest state of the art. The most important number in the search for life beyond Earth is uncertain by more than a factor of 10. If Eta Earth is 60%, then most sun-like stars have an Earth, and the nearest one is likely a stone's throw away in galactic terms. If it is 5%, the nearest genuine Earth analogue might be hundreds of light years off, and the entire architecture of every future telescope mission changes because you would need to survey far more stars to find anything at all. Why is the uncertainty so large? Because of everything we just described. Eta Earth is precisely the quantity our methods are worst at measuring. It sits at the exact corner of the parameter space, small planets on long orbits, where Kepler's sensitivity was falling off a cliff and where the sample of genuine detections is tiny. Estimating it means taking a handful of marginal signals at the edge of the noise, asking how many similar planets the survey would have missed, and extrapolating. Small differences in how you model the detection efficiency or how you treat the reliability of the faintest candidates, or how you define sun-like, or where you draw the boundaries of the habitable zone, cascade into answers that differ by an order of magnitude. There is nothing scandalous about this. It is careful people being honest about a hard measurement. But it does mean that when a documentary tells you there are 300 million habitable worlds in the galaxy, the correct response is to ask which end of that factor of 10 they used and whether they mentioned there was one. And there is a deeper problem lurking underneath, which is that the phrase habitable zone is doing an enormous amount of work in that sentence, and it is a far cruder idea than it sounds. Here is what the habitable zone actually means in its technical definition. It is the range of distances from a star at which the temperature would permit liquid water to exist on the surface of a rocky planet, given certain assumptions about the atmosphere. That is it. That is the whole definition. It is a distance band calculated from the star's brightness, and it says nothing whatsoever about whether the planet in question has water, or an atmosphere, or a solid surface, or any of the several dozen other things that seem to matter. Astronomers sometimes call it, a little ruefully, the Goldilocks zone. Not too hot and not too cold, and the nickname has done real damage because it makes people picture a comfortable green band when the reality is closer to a line on a map that says, if there is anything here, it will not necessarily boil or freeze immediately. The looseness runs deeper still. There is not one habitable zone, but several, depending on whose assumptions you use. The conservative habitable zone is narrow, the optimistic one is much wider, and it is derived by supposing early Venus and early Mars may have been habitable, which pushes the boundaries out at both ends. Whether a given planet counts as being in the habitable zone can therefore depend on which paper's definition you have picked up, and a good number of the worlds that have been announced with that phrase attached sit comfortably in one definition and outside the other. There is no dishonesty here. It is a genuinely fuzzy concept doing its best. But it means that a headline saying a planet is in the habitable zone conveys much less information than it appears to. And then, having established that the planet sits at a distance where water could in principle be liquid, you still have to ask everything else. Does it actually have water? Nobody knows for any of them. Does it have an atmosphere at all? For almost every one of them, nobody knows, and where we have checked, the news has often been bad. Is it a rocky planet or a small gassy one? Startlingly often, we cannot tell, and that is not a minor detail because the difference between a rocky world and a miniature Neptune is the difference between a surface and no surface at all. Does it rotate, or is one face locked permanently toward its star? Does it have a magnetic field to hold its air against the stellar wind? Does it have plate tectonics to recycle carbon and stabilize its climate over billions of years? Does it have a large moon? Did it get its water delivered, and did it keep it? We know the answer to none of those questions for any planet, anywhere, except this one. That is the thing I want to leave standing before we go further, because it reframes the whole subject. Every list you have seen of potentially habitable exoplanets, and there are such lists maintained seriously by good scientists, is a list of objects that satisfy roughly two criteria. Their measured radius or mass falls in a range that suggests rock rather than gas, and their orbital distance falls in a band where a certain model says water could be liquid. That is essentially all we have on them. Everything else, the oceans, the skies, the continents, the weather, the artist's impressions with the blue seas and the wispy clouds that accompany every press release, is imagination. Beautiful, well-intentioned, scientifically informed imagination, and imagination all the same. We have a size and an orbit. From a size and an orbit, we get a painting. I do not say this to be sour about it. The paintings are part of how a species learns to care about places it cannot reach, and caring is not a small thing. But tonight is an audit, and an honest audit has to note that the gap between what we have measured and what we have pictured is one of the widest in modern science. So let us go and stand on one of them, not a painting, as honest a version as the data allows. Let me take you to the instrument that found most of them, because the way it worked is one of the strangest and most patient things our species has ever done, and it deserves to be pictured rather than summarized. Kepler launched in 2009 into an orbit that trailed behind the Earth around the Sun, drifting slowly further from us each year so that nothing would block its view. And then it did one thing. It pointed at a single patch of sky in the direction of the constellations Cygnus and Lyra, a region about as wide across as your hand held at arm's length, and it stared. Not scanned, not surveyed, stared at the same field for 4 years. Picture the discipline of that. Every other great telescope moves. Hubble swings from target to target, thousands of them, a new object every few hours. Kepler did not move at all on purpose, because the entire method depended on measuring the brightness of the same stars in the same pixels with the same optics continuously, so that a change of 1 part in 12,000 could be attributed to a planet rather than to the instrument. Its job was not to take beautiful pictures. It never took a picture in the sense you would recognize. It measured the brightness of about 150,000 stars every 30 minutes for years and sent home a river of numbers. And inside that patch of sky mostly, nothing appeared to happen. That is the part I find remarkable. Night after night, month after month, the vast majority of those 150,000 stars simply sat there at constant brightness, and the data flowed back, and nothing was in it. The discoveries were not events. There was no moment when a planet appeared. There were only long columns of numbers in which, eventually after enormous processing, someone noticed that a particular star had been very slightly dimmer for a few hours, and then again exactly the same amount dimmer, exactly the same duration, a precise interval later, and then a third time. That is what finding a world looks like now. Not a glimpse through an eyepiece, a repetition in a spreadsheet. The instrument's ending is worth knowing too because it explains one of the limits we discussed. Kepler held its impossibly steady pointing using 4 reaction wheels, spinning flywheels that let a spacecraft turn and hold position without using fuel. In 2012, one failed. In 2013, a second failed, and with only 2 remaining, the telescope could no longer hold its stare. That was the end of the original mission at about 4 years, which is precisely the reason its sensitivity to Earth-like orbits was so marginal, since a planet with a 1-year period needs 3 years minimum to show 3 transits, and the margin for bad luck was almost nothing. Engineers then did something rather beautiful, working out that they could balance the crippled spacecraft against the faint pressure of sunlight itself, using photons as a third stabilizer. And Kepler flew on in that improvised mode for 4 more years, finding hundreds more planets until it ran out of fuel in 2018 and was retired. It is still out there, silent, drifting along its solar orbit. And here is the fact about Kepler's stare that I most want to leave with you tonight. That single patch of sky, the one it watched for years, covers roughly 1/400th of the celestial sphere, less than a third of 1%. And the stars in it are not the whole population either, only the ones bright enough and well-behaved enough to measure. So the great catalogue that reshaped our understanding of planets, the source of nearly every statistic in tonight's audit, the basis of every estimate of how many worlds the galaxy holds, came from staring very hard at a keyhole, which is a reasonable image for the whole enterprise. We have looked closely at a tiny fraction of the sky, using methods that see only a fraction of what is there, for a few decades. And from that, we are attempting to characterize 100 billion star systems. The wonder is not that our numbers are uncertain. The wonder is that we have numbers at all. Let this be tonight's first long stillness. Choose the most famous kind of habitable zone world we know of, because it is also the most common kind in the galaxy, and come stand on it with me for a while. The star is a red dwarf. This matters, and here is why it is the default setting for this thought experiment rather than a special case. Red dwarfs are small, cool, dim stars. and they are overwhelmingly the most abundant kind of star there is. Something like 3/4 of all the stars in the galaxy are red dwarfs. Not one is visible to your naked eye from anywhere on Earth, not a single one, because they are too faint, which is its own quiet fact about how unrepresentative the night sky is of the actual universe. And because they are so numerous and so small, they are where almost all of our nearby habitable zone planets have been found, including the ones you have heard of. So, you are standing on a rocky plain. The light is the first thing, and it is not like any light you have experienced. The star hangs in the sky noticeably larger than our sun looks from Earth, several times wider, because to be warm enough here, you must orbit very close in, far closer than Mercury orbits our sun, and it is deep red-orange, the color of an ember or a hot coal, because the star is cool as stars go. Everything around you is lit in that color. The rocks are the color of old brick. Your hands would look wrong. There is very little blue light here at all, which means that if there were plants, they would probably not be green, because green is what you are when you can afford to throw away the middle of the spectrum, and nothing here can afford that. Now notice what the sky is not doing. It is not moving. The star sits at a fixed point above the horizon, and it stays there. It does not rise. It does not set. It will hang in exactly that spot, at exactly that angle, for the rest of the planet's existence. Because you are orbiting so close, the star's tides have long since locked this world's rotation to its orbit, so it keeps one face turned inward permanently, exactly the way our moon keeps one face turned toward us. If you walk toward the star, you will eventually reach the point where it sits directly overhead, an eternal noon that has been going for 4 billion years. Walk the other way, and the star sinks toward the horizon, and then you cross a line into a night that has never once ended, where the ground is frozen and the sky holds stars that have never moved either. And along that boundary, that ring of permanent twilight the astronomers call the terminator, is where all the interesting speculation lives. If this world has an atmosphere, it is doing an enormous job, hauling heat from the scorched day side around to the frozen night side in winds that never change direction. And the terminator ring might be the one habitable band, a circle of eternal sunset going all the way around the planet. It is one of the most evocative images in modern astronomy, and it might be entirely real and nobody knows. But stand here a little longer, because we have to talk about what the star does. Red dwarfs are not gentle. It is easy to assume that a small, dim star is a mild one, and the opposite is closer to the truth. These stars are fully convective, churning all the way through, rather than having a calm, layered structure like our sun, and their magnetic fields tangle and snap violently. They flare. Not the modest flares our sun produces, but events that can briefly brighten the entire star by large factors in minutes, flooding everything nearby with ultraviolet and X-rays. And because your habitable zone is jammed right up against the star, you are not watching this from a safe distance. You are standing in it. So add that to the scene. Sometimes, without warning, the fixed red star in your unmoving sky flares white, and for a few minutes, the light is many times brighter and carries radiation that would sterilize an unprotected surface. Then it fades back, and it happens again, not once a century. On the most active of these stars, repeatedly, over billions of years, hundreds of thousands of times in the life of the planet. And that leads to the thing that has quietly reshaped this entire field over the last few years, because it stopped being theoretical. The question was always whether a planet like this could hold on to an atmosphere at all, given billions of years of that treatment plus the intense stellar wind of a close orbit. Theory said it would be hard. And then we got a telescope good enough to check. The system to check was TRAPPIST-1, a red dwarf about 40 light-years away with 7 rocky planets, 3 of them in the habitable zone, discovered in stages and announced to enormous excitement in 2017. It remains, by a distance, the best natural laboratory we have, because 7 transiting rocky worlds around one small bright enough star is a gift. The Webb telescope has been working through them. The results, so far, have been sobering. For the innermost planets, the ones closest to the star, the observations indicate that substantial atmospheres are unlikely. The measurements are consistent with bare rock, worlds that either never held an atmosphere or lost it long ago. For the habitable zone planet, the one everyone actually cares about, the picture is genuinely unresolved. And the reason it is unresolved is instructive in itself. The problem is that the star keeps contaminating the measurement. When you observe a planet's atmosphere in transit, you are looking at starlight filtered through the planet's air, which means you must first know exactly what the unfiltered starlight looks like, and a spotty, flaring, magnetically active red dwarf refuses to hold still long enough to be a reliable reference. The signal from the star's own blotchiness can imitate or mask the signal from a planetary atmosphere. Recent analyses of the habitable zone world have been able to rule out some possibilities, disfavoring an atmosphere dominated by hydrogen and leaving open the possibility of a thinner, nitrogen-rich one, while being unable to rule out the simplest option of all, which is that it has no atmosphere at all. Teams are now developing ingenious workarounds, including using the innermost, almost certainly airless, planet as a calibration reference for the star's own variability, and gathering many more transits. So here is where the most studied habitable zone system in the galaxy actually stands. After years of work with the most powerful telescope ever built on the best possible target, we cannot yet say whether the crucial planet has air. That is not failure. That is the actual difficulty of the thing made visible. And it is why the number at the start of tonight is 0. There is a piece of vocabulary that runs underneath this whole subject and almost never gets explained, and once you have it, A great deal of confusing news coverage suddenly makes sense. It is the difference between a candidate, a validated planet, and a confirmed planet. When a survey like Kepler sees a repeating dip in a star's brightness, what it has found is a candidate. Something is periodically blocking light. A planet is one explanation. It is not the only one, and the alternatives are more common than you would guess. The most troublesome is an eclipsing binary, two stars orbiting each other and passing in front of one another, which produces deep, regular dips. On its own, that would be obvious, because the dips would be enormous, but now put that binary pair in the background, far behind your target star, so that its light is diluted by the bright foreground star. A deep eclipse, watered down by the glare of an unrelated star in the same pixel, can imitate the shallow dip of a small planet almost perfectly. Telescopes have finite resolution, and a single Kepler pixel covers a patch of sky big enough to contain more than one star, so this happens constantly. There are other imposters, a grazing binary where two stars just clip each other, instrumental artifacts, cosmic ray hits, spacecraft pointing jitter, and the star itself with its spots rotating in and out of view, producing periodic brightness changes that have nothing to do with anything crossing it. So a candidate list is not a planet list. Kepler produced several thousand candidates, and the crucial work, occupying years and many careers, was sorting them. The gold standard is confirmation, which traditionally means detecting the same planet independently, usually by measuring the star's radial velocity wobble and finding a mass consistent with the size seen in transit. Two different physical effects, two different instruments, one consistent answer. That is a confirmed planet, and nobody argues. The difficulty is that for the planets we care most about tonight, confirmation is frequently impossible. A small planet on a long orbit around a faint, distant star produces a wobble far below what our spectrographs can measure. You can watch the transit all you like. You will never get the independent check. So the field developed the alternative, which is statistical validation. Instead of detecting the planet twice, you calculate the probability of every imposter scenario using everything you know about how many background binaries there are in that direction, how bright the star is, the shape of the transit curve, follow-up imaging to check for nearby contaminating stars, and so on. If the planet hypothesis is overwhelmingly more probable than all alternatives combined, typically by a factor of 100 or more, the planet is declared validated. Validation is legitimate, and it is how a large fraction of the 6,000 entered the catalogue. But it is a probabilistic argument, not a detection, and it carries two consequences worth knowing. First, a validated planet has a small but real chance of not existing, and when you validate thousands of them, a certain number are statistically guaranteed to be wrong, even if every individual analysis was done perfectly. Nobody knows which ones. Second, validation depends on models of the stellar neighborhood and the instrument, and if those models have a subtle flaw, the error is correlated across many objects at once, rather than being random. This is precisely the argument that has hung over the most Earth-like validated planets, the ones on long orbits around Sun-like stars, which are simultaneously the most interesting objects in the catalogue, and the ones where the transit signal is faintest, the number of observed transits is smallest, and independent confirmation is least available. Every property that makes a planet a good Earth analogue also makes it a hard object to be certain about. The overlap is nearly total. Our confidence is lowest exactly where our interest is highest. I find this genuinely poignant rather than frustrating. Nature has arranged the difficulty with a kind of dark symmetry. The planets that would matter most to find are the faintest, rarest, slowest, most easily faked, and least confirmable objects in the entire survey. If you had set out to design a universe that would make a young civilization work extremely hard for this particular answer, you could hardly have done better. Now let us go and visit the graveyard, because this is the part of the story nobody puts in the documentaries, and it is the most honest thing in tonight's whole audit. There is a long list of worlds that were announced in good faith by serious scientists as the most Earth-like planet yet discovered, and a striking number of them are no longer thought to be there. Begin with the one that got the loudest headlines of its era. In September of 2010, a team announced a planet around a nearby red dwarf called Gliese 581, and the planet, designated G, was reported to sit squarely in the habitable zone and to be roughly 3 or 4 times the mass of Earth. It was immediately and breathlessly described as the first potentially habitable exoplanet ever found. One of the discoverers was quoted saying the chances of life there were essentially 100%. It made front pages worldwide. Within weeks, another team analyzing a different data set could not find it. The argument ran for 4 years, and in 2014, a careful reanalysis identified what had actually happened, and the explanation is one of the most instructive in modern astronomy. The signal was real. It just was not a planet. It was the star. Red dwarfs are covered in star spots, cooler dark patches like sunspots, and as the star rotates, those spots move across its face and systematically distort the spectral lines that radial velocity measurements depend on. The result is a periodic wobble signal that has nothing to do with any planet and everything to do with the star's own rotation and magnetic cycles. When that stellar activity was properly modeled and removed, Planet G vanished. So did Planet D, another supposedly habitable world in the same system that had been announced earlier. 2 of the most famous potentially habitable planets ever found turned out to be, in effect, weather on the surface of a star. Then there is the one that got the phrase Earth's cousin attached to it. In 2015, NASA announced Kepler 452b, and it was genuinely exciting because, unlike almost everything else, it orbited a star quite similar to our Sun, at a distance quite similar to ours, with a year of about 385 days. The comparisons were irresistible and the coverage was enormous. But look at the technical language in the discovery paper, and you find the word validated rather than confirmed. and the distinction matters more than it sounds. Confirming a planet usually means detecting it independently by a second method. Validating it means running a statistical argument that no known alternative explanation is likely enough to account for the signal. For faint, long-period signals around distant stars, independent confirmation is often impossible with current instruments, so validation is what you get. And in 2018, a paper argued specifically that this planet, and others like it, could not be reliably confirmed by statistical validation alone, and that instrumental artifacts could not be excluded with confidence. It remains officially listed as a confirmed planet. It also sits under a genuine question mark, and it is a good deal less certain than the phrase Earth's cousin ever implied. It is also about 1.5 times Earth's radius, which, as we will see in a moment, may put it on the wrong side of a very important line. Even the nearest one carries caveats. In 2016 came the announcement that Proxima Centauri, the closest star to the Sun, has a planet in its habitable zone, and that remains one of the most extraordinary facts in astronomy, because it means the very nearest star to our own has a temperate world. But Proxima is a red dwarf, and a famously violent one, known for enormous flares, including at least one recorded superflare of remarkable size. Whether anything on that planet has held on to an atmosphere across billions of years of that is entirely unknown, and the detection itself is a radial velocity signal, which means we have never seen the planet transit, which means we cannot measure its atmosphere with current techniques even in principle. We know a minimum mass and an orbit. That is the whole file. Now, none of this is a scandal, and I want to be careful because it would be easy to tell this section as a story about scientists getting things wrong, and it is really the opposite. This is what a young field looks like while it is working correctly. Claims get made at the edge of the data. Other teams test them, some survive and some do not, and the ones that do not get retracted, sometimes by the original authors. That is the machinery functioning exactly as designed. The problem is not the science. The problem is the distance between the paper and the headline. A paper says, a candidate signal consistent with a planet of minimum mass so-and-so in the conservative habitable zone pending confirmation. The headline says scientists find second Earth, and the retraction 4 years later is not a headline at all, so the second Earth stays in the public mind long after it has left the catalogue. And there is one more downgrade, quieter and much broader than any individual world, and it may be the most consequential discovery in exoplanet science in the last decade. It concerns a line that turns out to run right through the middle of everything we thought we had found. For years, the catalogue was full of things called super-Earths, planets between 1 and 2 times the size of our own. They were exciting precisely because they had no counterpart in our solar system, and because a super-Earth in a habitable zone sounded like an Earth with more room. Then, astronomers gathered enough precise measurements to plot the sizes of small planets, against how many of each size existed, and the plot showed something nobody had predicted: a gap. Around 1.5 to 2 times the radius of Earth, there is a distinct valley, a size range where planets are noticeably rarer than on either side. It has become known as the Radius Valley, and the leading explanation is that it marks the boundary between 2 genuinely different kinds of object. Below it are rocky worlds with thin atmospheres or none, planets with surfaces, worlds you could in principle stand on. Above it are small planets that have held onto a thick envelope of hydrogen and helium, miniature Neptunes, worlds with no surface at all, where the atmosphere simply thickens downward into a crushing fluid, and there is nowhere to land. The consequence is severe for our census. A great many of the planets that were announced over the years as potentially habitable super-Earths sit at or above that line, which means a substantial fraction of them are probably not rocky worlds at all. They are small gas planets that were never habitable in any sense, and we had no way to tell the difference at the time because size alone does not distinguish them. And for most of these planets, size is all we have. The habitable planet count did not shrink because anything moved. It shrank because we learned to read our own catalogue better. Which brings us to the deepest problem of all, and the one that has produced the most dramatic scientific argument of the last 3 years. Suppose you get past every filter. Suppose you find a world that is genuinely rocky, genuinely temperate, and you manage to measure its atmosphere. How would you actually know whether anything lives there? The answer is that you look for a biosignature, a chemical in the atmosphere that life produces and non-living processes struggle to produce. And the search for one has just given us the clearest possible demonstration of how hard this is, in a story that unfolded in public over the last 3 years and is worth telling carefully, because it is the best case study we have. The world is called K218b. It orbits a red dwarf about 120 light-years away. It is about 8 or 9 times the mass of Earth and a bit over twice its radius, which places it, as you now know to notice, above the Radius Valley in the ambiguous country between Rock and Small Neptune. In 2019, it made headlines as the first habitable zone planet with water vapor detected, though that detection was later contested too, with some analyses suggesting the signal was methane rather than water. Then the Webb telescope looked at it, and in 2023, a team led by researchers at Cambridge reported something genuinely interesting. They found strong signatures of methane and carbon dioxide and an absence of ammonia, and they argued this combination was best explained by a new category of world they called a Hycean planet, a body with a deep global ocean of liquid water beneath a thick hydrogen atmosphere. If such worlds exist, they would considerably widen where life could live. And in the same analysis, they reported a tentative, weak hint of something else: dimethyl sulfide, a molecule that on Earth is produced almost entirely by marine life, particularly by phytoplankton. It is the smell of the seaside. Then, in April of 2025, came the announcement that made this a global story. The same group reported new Webb observations using a different instrument at different wavelengths and said the evidence for dimethyl sulfide and a related molecule had strengthened substantially, reaching about 3 sigma. The coverage was enormous, and to their credit, the researchers themselves were careful in the papers, describing it as the strongest evidence yet for possible biological activity outside the solar system, while explicitly stopping short of claiming life. And then the field did what the field is supposed to do. Other teams got the data. What followed over the next several months was a cascade of independent reanalyses, and they did not go well for the claim. Multiple groups, including a NASA-led team, reanalyzed the same observations, sometimes combining all 3 instruments' data rather than treating them separately, and found no statistically significant evidence for dimethyl sulfide. One reanalysis confirmed methane robustly at around 4 sigma, but found no significant support for either carbon dioxide or dimethyl sulfide. Others showed that the mid-infrared data in particular was highly vulnerable to unresolved instrumental systematics, meaning that features which look like a molecule can be produced by the detector rather than the planet. Analyses demonstrated that the apparent signal depended sensitively on which model assumptions you used, and that alternative molecules could fit the same data equally well. By late 2025, papers were appearing with titles stating plainly that the planet does not meet the standards of evidence for life, and the consensus had moved decisively away from the original claim. I want to be fair to everyone in this story, because it is easy to tell it as a debunking, and that is not quite right. The original team did careful work and published it with caveats. The critics did careful work and published that too. Nobody behaved badly. What the episode demonstrates is something more important than any individual result, which is the sheer difficulty of the measurement itself. Consider what is actually being attempted. You are looking at a star 120 light-years away. A planet crosses it, and during that crossing, a sliver of the starlight passes through the thin ring of the planet's atmosphere on its way to you. You are trying to detect the chemical fingerprint imprinted on that sliver, which alters the total light of the star by a few parts in a million, using an instrument in orbit, and then to distinguish one particular molecule from a dozen others with overlapping spectral features, in data where the detector's own quirks produce artifacts of comparable size. And then, having done all that, you must argue that no non-biological process could make the molecule, which requires knowing the chemistry of an environment that exists nowhere in our experience. The 3 sigma standard is worth a word here because it explains a great deal about how these stories go. 3 sigma sounds impressive, and it roughly corresponds to odds of about 1 in 300 that a result this strong arose from noise alone. In many fields that would be interesting. In physics, the conventional threshold for a discovery claim is 5 sigma, about 1 in 3.5 million, and the reason is precisely that 3 sigma results have a long and humbling history of evaporating when more data arrives. And for a claim as consequential as life beyond Earth, most researchers would want more than 5 sigma. They would want independent instruments, independent teams, and a demonstrated absence of any plausible non-biological explanation. Nothing in exoplanet science has ever come close to that bar. There is a broader lesson hiding in the biosignature problem, and it is one of the quiet frustrations of the field. Almost every molecule we might look for has a non-biological root. Oxygen, the most famous candidate, seemed like a sure thing for decades, because on Earth it is overwhelmingly produced by photosynthesis, and it is so reactive it would vanish in a geological instant without constant resupply. Then, modelers worked out several ways a lifeless planet can accumulate oxygen anyway, most straightforwardly by having its water vapor split apart by ultraviolet light from an active star, with the light hydrogen escaping to space, leaving the oxygen behind, which is exactly the situation around, of all things, a flaring red dwarf. So the single best biosignature we have may be systematically counterfeited in the very systems where we are most able to look. This is why serious astrobiologists talk less about finding a biosignature and more about assembling a case, multiple independent lines of chemical evidence in disequilibrium with each other, in a context where the geology and the star are well enough understood to rule out alternatives. That is a far higher bar than a single molecule in a single spectrum, and reaching it will require instruments we have not built yet. There is a further problem with the search that has nothing to do with instruments or biases, and it may be the most underappreciated item in tonight's whole audit. Even a perfect telescope pointed at a genuinely inhabited world might see nothing because of when it happened to look. Work through our own history, and the numbers are startling. Earth is about 4.5 billion years old, and life appears to have arisen astonishingly early, with reasonable evidence for living things within the first several 100 million years. So life has been here for perhaps 4 billion years, the overwhelming majority of the planet's existence. You might therefore assume that Earth has been visibly, detectably alive for 4 billion years. It has not. For roughly the first 2 billion years, life here was microbial, and the atmosphere contained essentially no free oxygen. A distant astronomer with a perfect spectrograph looking at Earth 2.5 billion years ago would have found nitrogen, carbon dioxide, methane, and no oxygen whatsoever. There was life in every ocean in enormous quantity, and the single biosignature we rely on most would have been entirely absent. Then, around 2.5 billion years ago, came what geologists call the Great Oxygenation Event, when photosynthesizing bacteria had produced so much oxygen that it finally overwhelmed the chemical sinks that had been absorbing it and began accumulating in the air. Even then, the rise was slow and staggered, and oxygen did not approach modern levels until a few 100 million years ago, at around the time complex animals appear. So, for something like half of the time life has existed on this planet did not look inhabited by the standards we ourselves apply. Half. If someone had surveyed Earth at a random moment in its history using the best biosignature we have, The odds of them catching us in the detectable phase would have been roughly a coin flip, and if they had looked during the first 2 billion years, they would have written us down as a lifeless world with an interesting atmosphere and moved on. Now extend the same logic forward, because it gets worse. The sun is gradually brightening as it ages, and in something like 1 billion years, the increased heat is expected to disrupt the carbon cycle and eventually boil the oceans away. Estimates for how long Earth's biosphere has left vary, but the general picture is that we are past the middle, which means the total window during which this planet is detectable as living, from the rise of oxygen to the end of the oceans, is perhaps a quarter or a third of the planet's total lifespan, and possibly less for the phase where the signal is strong. Fold that into the search. To detect a living world, it is not enough for the world to be habitable, and not even enough for it to be inhabited. It must be inhabited at a moment in its own history when its biology has visibly transformed its atmosphere, and you must be looking during that window, and the window is a fraction of the planet's life. Our own example suggests that fraction might be something like a third. So even in a galaxy generously seeded with life, a survey might find only a minority of the living worlds it examined actually announcing themselves, and would record the rest as barren. There is a mirror image of this problem that astronomers worry about too, which is the false positive rather than the false negative. A world could look convincingly alive and be entirely dead. We have already met the mechanism in the way ultraviolet light from an active star can split water and let hydrogen escape, leaving an oxygen-rich atmosphere on a sterile rock. So the two errors sit on either side of us. Living worlds that look dead for half their lives, and dead worlds that can be made to look alive by their star. Which is why nobody serious in this field expects a single clean moment of discovery. What they expect and plan for is a slow accumulation. A candidate with an intriguing spectrum, years of follow-up, arguments in the literature, other teams reanalyzing, additional molecules sought and found or not found, models of the star, and the geology built up until the alternatives can be excluded one by one. The announcement of life beyond Earth, if it comes, will most likely not be an announcement at all. It will be a gradual hardening of consensus over a decade or more, until at some point people notice that the argument has stopped, and everyone has quietly started saying yes. It is a less cinematic ending than the film's promise. I think it is a more moving one because it is the shape of every real thing humanity has ever come to know. There is a way to make all of this concrete, and it is my favorite thought experiment in the whole subject. So let us do it properly. Turn the telescope around. Instead of asking what we can see of them, ask what they could see of us. Put an astronomer on a planet 100 light-years away, give them our technology, exactly what we have tonight, no more, and point them at the sun. What would they find? The first thing to establish is whether they could find Earth at all, and the answer depends entirely on where they happen to live. As we said, the transit method requires alignment, and the odds of a randomly placed observer being positioned to see Earth cross the face of the Sun are roughly 1 in 200. So for 99.5% of the observers in the galaxy, Earth simply never transits. It casts no shadow their way. It is, to their surveys, absent. There is a narrow band across the sky, a strip aligned with the plane of our solar system from which Earth is detectable by transit at all, and astronomers have actually mapped it and identified the stars that currently sit inside it, which is a charming and slightly unnerving piece of work. If our hypothetical observer is not in that strip, they can watch the Sun for 1,000 years with perfect instruments and never know we are here. Say they are lucky. They are in the strip. Now they must detect a dimming of 1 part in 12,000, lasting about 13 hours once per year, and they must catch it at least 3 times to be confident, so they need at least 3 years of continuous observation of our star without a gap that happens to fall on the transit. Suppose they manage it. What do they now know about Earth? They know its size from the depth of the dip. They know its year from the interval. From the year and the Sun's properties, they can calculate its distance, and from the distance they can put it in their habitable zone diagram. That is the entire haul. At this point, Earth enters their catalogue as an Earth-sized planet in the habitable zone of a G-type star. And, if their science journalism is anything like ours, somebody writes an article with a painting of an imagined ocean world. Notice, they do not know it has oceans. They do not know it has an atmosphere. They do not know it is not a bare rock like Mercury, or a runaway greenhouse like Venus, which from their vantage point would look almost identical, because Venus is nearly the same size as Earth and sits at the inner edge of the same habitable zone. If our observer detected both Venus and Earth, they would have 2 habitable zone planets in their catalogue, and no way whatsoever to tell that one is a paradise and the other is a lead-melting hell with clouds of sulfuric acid. Think about that whenever you see a list of potentially habitable worlds. Our own solar system contains a beautiful example of exactly how wrong such a list can be, and the wrong entry is our nearest neighbor. Could they go further and read our air? To do that, they would need to catch the starlight filtering through the thin ring of our atmosphere during transit, and here the numbers become brutal. Earth's atmosphere is a shell only a few tens of miles thick around a planet 8,000 miles across, which means the atmospheric signal is a tiny fraction of an already tiny transit signal. Studies of this question generally conclude that detecting the atmospheric composition of an Earth-like planet around a Sun-like star at interstellar distances is beyond the reach of a telescope like Webb, requiring impractical numbers of transits stacked together. Webb can do this work for planets around small, dim red dwarfs, where the planet is proportionally much larger against its star, and the transits come around every few days instead of once a year. For an Earth around a Sun, it is out of reach. Our observer, with our technology, could not determine that our air contains oxygen. They could not detect our biosphere. They could not detect us. Sit with that, because it is the honest answer to why our count is 0. It is not that Earths are absent. It is that a civilization with our exact capabilities, looking at the one planet in the universe we know for certain is inhabited from a typical distance, would almost certainly fail to detect the life on it, and would most likely fail to detect the planet at all. We are not looking at an empty sea. We are fishing with a net that could not catch our own planet. And that reframes every number in tonight's audit. When we say we have found no Earths, we have said something about our instruments, not about the galaxy. When someone says the silence is evidence of rarity, the honest reply is that we have not yet run the experiment that could detect ourselves. The search has been going for 30 years, which sounds like a long time, and in the time scale of the question, it is nothing at all. There is a version of this thought that goes the other way too, and it is worth a moment because it is genuinely humbling. Suppose there is an observer in that lucky strip, right now, with instruments considerably better than ours. What would they see? They would find a small rocky planet with an atmosphere containing oxygen at 21% alongside methane, two gases that react with each other and should not coexist unless something is continuously replenishing both. That combination, oxygen and methane together in serious quantities, is about the best biosignature anyone has ever proposed, precisely because it is so difficult to explain without a biosphere. They would see the light reflected off our planet change color slightly through the year as the great northern forests leaf out and die back, a signal astrobiologists call the red edge. And in the last century or so of that record, they would find traces of industrial compounds that have no natural source whatsoever. Everything we are hoping to detect somewhere else, our own planet has been broadcasting continuously for hundreds of millions of years into every direction at once, entirely without effort. The signal exists. The question tonight has never been whether such signals are out there. The question is whether anyone has built an instrument capable of reading one, and we have not yet. So what would it actually take? What kind of machine could find another Earth and read its air? And does it exist? And when? The answer requires abandoning the transit method entirely, because, as we have just seen, it will never be the tool for this job around sun-like stars. Transits give you a 1 in 200 chance of alignment and an atmospheric signal too faint to read. To genuinely characterize an Earth twin, you have to do the thing that sounds simplest and is by far the hardest. You have to see the planet itself. Direct imaging. Collect actual photons that bounced off the planet's surface and clouds and spread them into a spectrum and read what the atmosphere absorbed on the way out. The obstacle is glare, and the scale of it is difficult to convey. A planet like Earth shines only by reflected light, and it is a small object next to an enormous furnace. Invisible light, Earth is something like 10 billion times fainter than the Sun. And from 100 light years away, that fantastically faint object sits an almost immeasurably small angle away from the blinding one, closer in apparent separation than a coin held at the far end of a long field. The standard comparison in the field is trying to photograph a firefly hovering beside a lighthouse from many miles away, with the lighthouse lit. Ordinary optics cannot do it, not because the planet is too faint to detect in absolute terms, but because the star's light scatters and diffracts inside the telescope itself and drowns everything nearby in a haze of its own glare. There are two ways to beat it, and both are magnificent. The first is a coronagraph, an instrument inside the telescope that uses precisely shaped masks and mirrors to cancel the star's light through interference, sculpting a dark hole in the glare where a planet can be seen. Building one that achieves 10 billion to 1 suppression stably on a telescope in space requires mirrors controlled to a fraction of the width of an atom and is one of the genuine frontiers of optical engineering. The second approach is even more audacious. Fly a separate spacecraft, a giant, precisely shaped, petal-edged screen tens of meters across, tens of thousands of miles in front of the telescope, positioned so that it casts a shadow of the star directly onto the telescope, while letting the planet's light around the edge. A starshade. Two spacecraft flying in formation across tens of thousands of miles, aligned to within a meter or so, repositioning for days every time you want to look at a different star. And there is a mission being designed to do this. It is called the Habitable Worlds Observatory. It was the top recommendation of the American astronomy community's most recent decadal survey, and its stated purpose is precisely tonight's subject. It is planned around a primary mirror roughly 6 meters across, with the explicit goal of directly imaging and searching for biosignatures on at least 25 potentially habitable worlds around sun-like stars. 25. That is the target, not thousands. The mission is designed to answer, for a couple of dozen nearby stars, the question we have never once been able to answer for any star. The timeline is the sobering part. The Habitable Worlds Observatory is currently aimed at a launch in the mid-2040s. That is not a delay or a scandal. It is simply what building an instrument of this class takes. And Webb itself is the cautionary example, having taken decades from concept to launch. So, the honest answer to when we will find another Earth is that the machine capable of doing it is presently a set of drawings and technology development programs, and if everything goes as intended, it will begin observing sometime in the decade after next. Which means something rather moving, and I want to state it plainly because it is the human shape of tonight's story. The question of whether there is another living world is almost certainly answerable. It is not a mystery in the sense of being permanently beyond us, like what came before the Big Bang. It is an engineering problem with a known solution and a price tag. We know what to build. We are building it. And the answer will arrive, most likely, within the lifetime of most people listening tonight, but not soon. and not from anything currently in orbit. There is a decent chance that the person who will one day sit in front of a spectrum of another living world's atmosphere and be the first human being to know is alive right now and has not finished school. And the 2040s is not the whole story, because there is a great deal happening before then. And the next decade is arguably the most interesting stretch this field has ever had. Several missions are either flying now or about to. One European observatory is designed specifically to hunt for Earth-sized planets in the habitable zones of bright, sun-like stars using the transit method, going after exactly the population Kepler could only glimpse, and doing it around stars near enough and bright enough for follow-up work to actually be possible, which was Kepler's great limitation, since most of its discoveries orbit stars too faint to study further. Another is built to survey the atmospheres of a large sample of known planets systematically, rather than one at a time as Webb must, which will finally give us population-level chemistry instead of anecdotes. A large infrared observatory now nearing launch carries a technology demonstration coronagraph intended to prove, in space, the starlight suppression techniques that the Earth imaging mission will later depend on. None of these will find an Earth twin and read its air. All of them are the necessary staircase, and Webb itself has years of work ahead. Its great strength, as we saw with the TRAPPIST system, is rocky planets around small dim stars where the geometry is generous. The next several years will steadily settle the question of whether such worlds keep their atmospheres at all, and that is not a small question, because 3/4 of the stars in the galaxy are red dwarfs. If the answer turns out to be that planets around small stars are systematically stripped bare, then the habitable real estate of the galaxy shrinks dramatically overnight, and the search narrows to sun-like stars, which are rarer and much harder to work with. If the answer is that some of them hold on, the number of potential homes in the galaxy multiplies enormously. That single question, which nobody could even have asked 10 years ago, is being actively decided right now, with data being taken this year. It is also worth knowing that the answer may arrive from an unexpected direction, because the ground has been catching up. A generation of extremely large telescopes is being built on mountaintops right now, with mirrors of 25, 30, even 39 meters, vastly larger than anything in space, using adaptive optics that reshape a deformable mirror hundreds of times a second to cancel the blurring of our own atmosphere. Those instruments will not be able to image an Earth around a sun-like star. The glare problem is too severe from the ground, but they may well be able to study rocky planets around the nearest small stars in far more detail than Webb can manage, and some of them are designed with the specific hope of detecting oxygen in the atmosphere of a temperate planet around a nearby red dwarf. It is possible, genuinely possible, that the first strong biosignature candidate comes from a mountain in Chile rather than from space. So the field is not waiting idly. It is building on two fronts the instruments that this audit says are required. And in the meantime, the honest number stays where it is. It is worth saying clearly that direct imaging is not purely a future technology. We have done it, just not for anything remotely like Earth, and the gap between what we can image and what we need to image is the last piece of tonight's audit. The planets we have successfully photographed share a very specific profile. They are enormous, several times the mass of Jupiter. They orbit far from their stars, often further than Neptune orbits ours, so the glare is less overwhelming. And crucially, they are young, only a few million years old, which means they are still glowing with the leftover heat of their own formation, radiating in the infrared like dying embers. That last point is the trick. We are not seeing reflected starlight from these worlds. We are seeing their own heat. They are self-luminous, and that makes them perhaps 1,000,000 times easier than a cold, rocky planet that shines only by the light it bounces. The most famous example is a young star catalogued as HR 8799, where astronomers have imaged 4 giant planets at once and have watched them long enough to assemble actual footage of them moving along their orbits. There is a short video compiled from images taken over years in which you can watch 4 alien worlds visibly circle their sun. If you have never seen it, it is worth looking up in the morning. It is one of the genuinely astonishing artifacts of modern science, and almost nobody knows it exists. But now measure the distance between that achievement and tonight's target. Those planets are giants. We need something the size of Earth. They orbit far out. We need something in close where the glare is worst. They are young and self-luminous. We need something old and cold that shines only by reflection. Each of those factors makes the problem harder by a large factor, and together they multiply into the 10 billion to 1 contrast we discussed. Imaging a giant young planet on a wide orbit is to imaging an Earth twin roughly as photographing a bonfire on a distant hill is to photographing a single candle held beside a searchlight. So the achievement is real and the gap is real, and both should be held at once. There is one more image worth bringing into this, and it is the oldest and simplest, and I have been saving it. In 1990, as the Voyager 1 spacecraft left the planetary region for good, the mission turned its camera around at Carl Sagan's urging and over some engineering objection, and took a final portrait of the solar system from about 4 billion miles out. In one of those frames, caught by chance in a band of scattered sunlight inside the camera, there is a single pale dot occupying less than a pixel. That is Earth. Photographed from inside our own solar system, from a distance light crosses in about 5.5 hours, our planet is a fleck less than 1 pixel across, and it is only visible at all because the camera happened to catch it in a shaft of glare. Now hold that next to tonight's problem. That is what our planet looks like from 4 billion miles. The nearest star is more than 6,000 times further away than that photograph was taken from. And a typical target for the future telescopes we discussed will be dozens of light years off, which is millions of times further still. That is the object we are trying to find around other stars, not a world with visible continents. a sub-pixel fleck 10 billion times fainter than the fire beside it, at a separation so small that no telescope yet built could split them apart, whose atmosphere we then propose to read. When you frame it that way, the fact that serious people have designed a workable mission to do this, and that it has been endorsed as the top priority of an entire scientific community, stops sounding like a slow timeline and starts sounding like an act of considerable nerve. We are proposing to photograph the pale blue dot of another star, and then to determine what its air is made of from across the galaxy's local neighborhood. We may well manage it. That is the extraordinary part. Nothing in physics forbids it. The engineering is understood, and the main obstacles are budget and patience. But it is worth understanding when you hear that we have not yet found another Earth, that this is the actual size of the task that has not yet been completed. There is one more layer to tonight's audit, and it is the deepest and the strangest, because it is not about telescopes at all. It is about the fact that we do not actually know what we are looking for. Here is the difficulty, stated plainly. We are searching for planets like Earth, because Earth is the only planet we know of that has life. But we have exactly one example. One. In every other field of science, drawing conclusions from a sample size of one is understood to be nearly worthless, and we would never accept it. And yet, the entire architecture of this search rests on it, because it is all we have. Every criterion on the checklist, the liquid water, the rocky surface, the moderate temperature, the atmosphere, is derived by looking at ourselves and assuming we are typical. And we have no way at all to check whether we are typical because there is nothing to compare against. Which means the list of requirements is really a list of the properties of home. And honest scientists will tell you they do not know which items on it are genuinely necessary and which are simply true of us. Consider how long that list has become. Liquid water, presumably. A rocky surface, we assume. But then people started adding, and the additions are all reasonable and none of them are proven. A magnetic field generated by a churning molten core to deflect the stellar wind that would otherwise slowly strip the atmosphere away. Plate tectonics, which on Earth runs a carbon cycle over hundreds of millions of years, that acts as a planetary thermostat, drawing carbon dioxide down into rock when things get warm, and returning it through volcanoes when things get cold. Without it, some models say, a planet's climate wanders and never stabilizes long enough for complex life. A large moon, which stabilizes the tilt of our axis and prevents the chaotic wobbling that would otherwise swing the poles wildly over millions of years. A giant planet further out, which may have shepherded or deflected some fraction of the comets and asteroids that would otherwise have arrived here. The right amount of heavy elements in the star that formed it, since a star too poor in metals may not build rocky planets at all. Even a position in the galaxy that is neither too close to the crowded, radiation-soaked center, nor too far out in the metal-poor suburbs, an idea called the galactic habitable zone. Every one of those is a genuine scientific proposal with genuine arguments behind it. And the honest status of every single one is the same. We do not know if it is required. We know only that we have it. You can see how the two possible errors sit on either side. If we are being too strict, if life is far more accommodating than our one example suggests, then we are walking past living worlds constantly because they do not look enough like us. Maybe life thrives under the ice of moons with no sunlight at all, of which our own solar system contains several excellent candidates. Maybe the Terminator ring of a tidally locked red dwarf world is teeming. Maybe there are biospheres running on chemistries we have not thought of, in conditions we have crossed off the list. And if we are being too lax, if the real recipe requires nearly everything on that long list to line up at once, then Earths in the meaningful sense might be extraordinarily rare, and the galaxy could be full of temperate rocky planets that are all as dead as Venus. Both of those are live possibilities tonight. Nothing in the data currently rules out either one. That is not a failure of the scientists. It is what the beginning of a field looks like. And I find something genuinely beautiful in that, which is worth saying at this hour. We have spent tonight walking through a long catalogue of things we do not know, but every one of those unknowns is a question that can be answered, and most of them are questions nobody could even have formulated 50 years ago. Nobody in 1970 could have asked whether there is a radius valley separating rocky planets from mini Neptunes, because nobody knew of any planet outside our solar system to have a radius. Nobody could have argued about the reliability of a dimethyl sulfide detection at 3 sigma, because there was no spectrum of any exoplanet atmosphere to argue about. The questions themselves are an achievement, a field that has gone from 0 known planets to 6,000, and from no atmospheric measurements to a public scientific argument about the chemistry of a specific world 120 light-years away, in the span of a single human career, is not a field that is failing. It is a field that is moving faster than almost any other in the history of science, and simply has not arrived yet. So let us gather the audit, because we now have everything we need to state the honest answer to tonight's question. How many worlds like ours are actually out there, confirmed, measured, verified to be rocky and temperate, with an atmosphere we have actually read and a composition consistent with the one place we know life exists? 0. Candidates that satisfy the two crude criteria of plausible size and plausible orbital distance, a few dozen that are frequently listed depending on whose definition of the habitable zone you adopt and how generously you treat the size cutoff. Statistical estimates of how many exist in the galaxy, extrapolated from a biased catalogue by careful modelling, somewhere between a few 100 million and several billion, with the crucial fraction uncertain by more than a factor of 10. Number of those we have ever seen as anything but a shadow or a wobble? None. Number whose air we have successfully read? None. Number we could detect with present technology, even if it were an exact duplicate of Earth orbiting a sun-like star at a typical distance? Effectively, none. That is the state of the census, in full as of tonight. And underneath even that sits the oldest assumption of all, the one so foundational, that it is written into the definition of the habitable zone itself, and it deserves examining before we close the audit. Why water? The reasoning is genuinely good and worth knowing rather than simply accepting. Life, as far as we understand it, requires a solvent, a liquid in which molecules can dissolve, move about, encounter each other, and react. A solid is too rigid for chemistry to happen at useful speed, and a gas is too diffuse for complex molecules to find each other reliably. A liquid is the middle state where chemistry gets interesting, and water is an exceptional solvent by several measures. It dissolves an extraordinary range of substances. It remains liquid across a wide temperature range. It has an unusually high heat capacity, so it buffers temperature swings. And it has the very strange property of expanding when it freezes, so ice floats. So bodies of water freeze from the top down and insulate what is below rather than freezing solid from the bottom up and killing everything in them. That last property is genuinely peculiar, and if water behaved like nearly every other substance, the history of life here would have been very different. Water is also helpfully made of the first and third most abundant chemically active elements in the universe, so it is everywhere. We find it in comets, in interstellar clouds, in the atmospheres of gas giants, in the plumes of icy moons. It is not a scarce or exotic substance. It is one of the most common molecules there is. So the case for water is strong, and the case for carbon alongside it is similarly strong, because carbon forms 4 bonds and builds long, stable chains and rings in a way no other common element manages, which is why the chemistry of life is called organic chemistry. Given all that, focusing the search on carbon and water life at temperatures where water is liquid is not narrow-mindedness. It is the sensible strategy of looking where you actually know how to look. And yet, it is still the sample of one wearing a lab coat. Chemists have sketched alternatives, and they are not absurd. Ammonia is liquid over a range far colder than water and could conceivably host a slower chemistry. Liquid methane and ethane, which exist in genuine seas on Titan in our own solar system, at close to 200 degrees below zero, have been proposed as a solvent for a chemistry we cannot yet imagine in any detail. Supercritical carbon dioxide has its advocates. None of these has any evidence behind it whatsoever, and most chemists consider them substantially less promising than water. But less promising is not the same as impossible, and the honest position is that we do not know whether life requires water or whether life simply happened to use water here, because here had water. The deeper version of the problem is that we do not know how life started even once. Not really. We have candidate mechanisms and suggestive laboratory results, and no accepted account of the path from ordinary chemistry to the first self-sustaining, replicating system. And you cannot compute the probability of an event whose mechanism you do not know. That is not a gap in the data, it is a gap in the theory, and it means the crucial term in every estimate of how much life exists in the galaxy is not merely uncertain, it is undefined. People plug numbers into it, and the numbers are guesses dressed in decimal points. So here is the audit's final and most honest column. We can now count planets, and we are getting good at it. We can measure the atmospheres of some of them, and we will get better. Both of those are engineering problems yielding steadily to effort. But whether a temperate, wet, rocky world reliably produces life, or almost never does, is not a question our telescopes can answer at all. It is a question about chemistry and probability that would remain open even if we had a perfect map of every planet in the galaxy. The only thing that will settle it is finding a second example. One more, anywhere. A living world around another star, or, just as decisively, an independent origin of life somewhere in our own solar system, under the ice of Europa or Enceladus, or in the ancient rocks of Mars. That is the actual prize, and it is worth being clear about it. We are not looking for another Earth because we want a place to move to, whatever the headlines suggest. We are looking because the number 2 would change everything. One example tells you nothing about how common something is. 2 tells you it happens more than once, and a universe where life happens more than once is a categorically different universe from the one we can presently prove we live in. And now let us turn it over, because a 0 can be read 2 entirely different ways, and which one you choose is not really a scientific question. It is a temperamental one, and I would like to offer you the reading I find more honest as well as more comforting. The pessimistic reading says the 0 is meaningful. It says we have looked at 6,000 worlds and found nothing like home. And perhaps that is because home is a fluke, an improbable accident of chemistry and position and history, and the galaxy is full of temperate, dead rock. That reading is not stupid, it might be right, but tonight's audit has shown you exactly why it is premature, and the reason is the fisherman with the 4-inch net. We have not searched and failed. We have searched with instruments that are constitutionally incapable of finding the thing we are looking for, and we have found, unsurprisingly, that we did not find it. Our 0 contains almost no information about the galaxy. It is a statement about the years 1992 to 2026, and about 2 detection methods, and about the size of mirrors we have managed to put into space so far. The optimistic reading is simply the arithmetic run forward. Every barrier we have described tonight is technological, and technology moves. 30 years ago, the count of known exoplanets was 0, and the honest position was that we might never find any. Today it is 6,000. We routinely measure the chemical composition of atmospheres around other stars, and there is a mission on the drawing board built explicitly to photograph Earth twins, line those points up, and the curve is not flat. It is one of the steepest curves in modern science, and it is still climbing. But there is a third reading, and it is the one I actually want to leave you with, because it is not about the galaxy at all. For the whole of tonight, one planet has sat quietly at the center of the audit as the reference standard, the definition, the thing every other world is measured against and found wanting, ours. And notice what that means. When astronomers list the criteria for habitability, they are describing this place. When they build a telescope to search for another world with liquid water and a stable climate and an oxygen atmosphere and a magnetic field and a moon, they are building an instrument to look for a copy of the ground beneath your bed. Earth is not merely one of the candidates. Earth is the entire specification, the sample of one, the only confirmed habitable world in a survey of 6,000. We spend a great deal of effort looking outward for something that might resemble what is already, verifiably, here. And the search is worth every penny, and I hope it succeeds in our lifetimes. But there is a particular quiet that comes from noticing that the rarest and most extraordinary object in tonight's entire catalogue is the one you are lying on. So here, at the end of the audit, is the cascade. It was never a story about absence. We did not find another Earth because our best method needs a 1 in 200 alignment and misses the rest. We did not find another Earth because the signal is 1 part in 12,000 and it arrives once a year, and you need 3 of them. We did not find another Earth because a wobble of 9 centimeters per second hides inside a star that is boiling. We did not find another Earth because half the worlds we called super-Earths turned out to be small Neptunes with no ground at all. We did not find another Earth because the most promising candidates orbit stars that flare, and we cannot yet tell whether their air survived. We did not find another Earth because the one biosignature everyone agreed on turned out to have a counterfeit. And we did not find another Earth because, with the instruments we currently possess, we could not find this one either. None of that is the universe being empty. All of it is a species 30 years into a search, holding the very first generation of the right tools, discovering how much harder the problem is than it looked, which is the ordinary and honorable condition of anyone at the beginning of something worth doing. Thank you for spending this night going carefully through the numbers with me, through the nets and the biases and the graveyard of retracted worlds. I know an audit is a stranger thing to fall asleep to than a tour, and I hope the honest version was worth it. If sleep has been circling while we talked, let it land now. Nothing tonight is unresolved in any way that needs you. And if you are still here at the end, one last thing to take down with you. Somewhere out in the strip of sky aligned with our orbit, there may be an astronomer on a world we will never see, watching our sun, waiting for a shadow. Once a year, for 13 hours we cross, a dip of 1 part in 12,000. It is the smallest possible announcement, and it has been going out faithfully in every direction for 4.5 billion years, whether or not anyone was ever there to notice. Tonight, you are lying on the object that makes it. Sleep well on the only confirmed habitable world in the known universe. Good night.